everyone, this is my fourth video for the Sparks Foundation GRIP program July. This video is going to be on color identification in images. So I am using a public data set which I got from Kaggle. It's over here. So what this has is folders names with that type of color, and each folder contains images which act as the training data for that color. So the first thing you do is you import the necessary libraries. In this, CV2 is used for the image recognition, and OS is used to just get the images, get the file path. So you have the data directory, which was the color classification folder as I showed. These were the categories that you take. This is just a function to get the array of the images that you're going to find in those directories. So what you do is you create the training data, which is a list which contains one, the array of the image, and two, the name, the category of that image. There are 107 examples, and the images of 100 cross 100 cross 3. The 3 represents RBGs. The image size we declared over here. What you're going to do next is, from this training data, you separate out the X, which is basically the image data, and the Y, which is the target variable. So as you can see, this is 107 cross 100 cross 100 cross 3, and this is 107. Next, you flatten the arrays because these are in nits. So you divide it by 255. So the highest brightness you can have is 255. So you divide it by this. And since this is going to be one number from 0 to 7, I thought it would be best to convert it into a categorical data and use it after getting the categorical data. It's just better because I didn't have to worry about what kind of activation function I was going to use. It could just use probabilistic methods. So yeah, I just thought this would be better. So the next thing that we did was import Keras models and Keras layers. So from Keras we got the convolution 2D, max pooling 2D, dense, flatten, and dropout layers. The first thing we do is that we add a filter of 32 size with a kernel size of 5 by 5. So what this is basically saying is that you have a small window which is going to pass over all the pixels in the input, and it's going to use convolutions to fit it into the next layer, which is going to go to the max pooling layer. So what they're going to do is they're going to take the max values of the windows that you have created, and they're going to size it down. So you size down, you max pool, you again use the convolution, max pool, and then there is a dropout layer so that it doesn't rely too much on this. This will basically help you to prevent overfitting. Then you flatten it. So now you have okay, I didn't show model.summary. So flattening, what it basically does is, since this was a 3D data, it is finally converted to 2D data, which has a lot more information that the model can now work with, the algorithm can now work with. So after that, we use the dense layers to finally get to a soft wax layer, which is going to give you 8 categories. These 8 categories, they're basically 0, 0, 0, 0. They're one-hot encodings or dummy types, which are going to be matched with the target variable. The activation function in most of these is ReLU, except for the last one, which is going to be probabilistic. The input shape is xShape.1, which is basically 100, 100, and 3. The loss function used is categorical cross entropy, Adam optimizer, and we're using accuracy to measure how the model is going to be performing. Each epoch took about a second instead for the first one, which took 17 seconds. As you can see, the loss is decreasing and the accuracy is increasing. We eventually had an accuracy of 97%, which is the best that we've had, with a validation accuracy of 100% and a loss of 0.1022. This is it for this video. I'll see you in the next one.